All right, welcome back to Physics 4C Lab. This week we are going to be looking at interference of light, something we've been talking about in lecture. So in lecture, in chapter 34 and 35, we have introduced different examples of where interference takes place. One of the most common examples that we've looked at in the chapters is when we have narrow slits, some kind of a barrier set up, we're shining light at it, and then within the barrier we've placed a series of narrow slits. Now, what we're going to be doing in lab is making use of these plates right here. These are some plates in which we have some precision series of narrow slits set up. Some of these slit patterns have just a single slit with some width to it, and then other patterns have multiple slits with some distance of separation. So let's take a look at the pattern that we have here. We're not going to do measurements on all of these. We're going to be doing measurements, it looks like about half of them. Again, a reminder, the tidal light interference, the objective is we want to be able to go in on this plate and measure the slit widths. So we want to be able to measure width A. And we also want to be able to measure distance between adjacent slits. So the multiple slit examples on here have even spacing between the slits, and we can go in and measure that also. So if you're thinking this sounds kind of like homework problems, that's a good sign. That means you're staying caught up with everything, and this should sound very familiar. So again, I'm everybody's lab partner, and again, I'm a good lab partner to have because I am caught up. I've been doing all my reading. I've been watching all the lectures. I am caught up with all the homework problems, and this looks like it's going to make sense to me. Looks like it's not going to be such a, I think it might actually be kind of an interesting lab. So, which they all are, right? They're all interesting labs. So this is just another example of one. So here's how the plates are organized. There's 5 columns, there's 5 rows. I've labeled the columns A, B, C, D, E for some reason. And I've labeled the steps 1, 2, 3, 4, 5. Let's see. So along column A, everything along column A is a single slit. There are slits with different widths. And so the intention is, hey, we could go in and measure the effect of changing the slit width when there's just one slit. That would be pure diffraction, just diffraction alone that we'd be taking a look at. So there's different types of interference effects, and diffraction is one of those. And that would be looking at just pure diffraction sort of interference effects. So here's just straight diffraction. Now, it turns out that these are actually kind of difficult measurements to make. I'm just going to say let's do 3, 4, and 5 in column A. That's enough. So we'll be able to see the effect of what happens when the slit width is increased gradually. All right. So we're going to be, those are 3 that we have to do as measurements. There's going to be data tables set up for those. And then there's this column B, which is a variable width that kind of extends across the whole plate. We're not going to use that at all. So you can ignore column B. When we get to column C is really nice because I'm going to say these are the easiest measurements of all. So the measurements that we do along column C, I think are like, they're the easiest ones. What they are is they're multiple slits, many slits. They got like 10 or 15 or 20 different slits. So they start to look like diffraction gratings. Now, if you remember from chapter 35, once we've done diffraction gratings really shouldn't be called diffraction gratings. That's just confusing. It's not based on diffraction. It's based on multiple slit interference. So 2 distinct types of interference effects. So they got the name wrong with diffraction grating. In any case, we can call it a grating because what it ends up looking like when you place a bunch of these narrow slits next to each other, it looks like a grating, right? There's a bunch of openings and they're all parallel and they're all kind of shaped like slits. All right, so these are multiple slits examples, and I'm going to say we have to do them all. These are the easy ones. Why not do them all? C1, C2, C3, C4, C5. We'll collect data for all of those. Now, when we get to, I'm going to jump to column E. I'm going to skip D for right now, because along column E are specifically examples with two slits. So two slits is kind of how we started off this interference discussion back in chapter 34. So again, those are probably some that you have. Maybe that's the most familiar type of interference that we've looked at so far. And along column E, what they're doing is they're changing the distance between the slits. They're keeping the widths the same, but they're changing the distance between them. Now, what does happen with all of these is that since even in this two-slit case, the slits themselves still have width. And so that means that there's always a diffraction effect going on. If I was over here in column A, where there's only one slit, then it would be purely a diffraction effect. And this is the intensity pattern that we would see, and I guess I should add that to the graph here. This is intensity as a function of, I'm going to call this N. Now, it's not index of refraction. It's keeping track of, well, it's the same stuff we talked about in lectures. So it's keeping track of phase differences between the different slits. And over here, for multiple slits, this also is an intensity function sort of drawn out here. And the intensity function here I'm going to write as a function of M. So when we have pure diffraction, this is the only thing going on, and this is the intensity formula that we had derived in class. But when we have multiple slits, whether it's 2 or 3 or 4 or 10 or 15 or 20, then we start to get these peaks at the integer values of M with little smaller peaks inside. Now, sometimes, depending on how many slits there are, if there's only 2 slits, then there aren't going to be any little peaks inside at all. And then as you go to 3, 4, 5 slits, you're going to see the number of intermediate peaks go up, but we'll see that in column D in just a minute. So in column E, we've got 2 slits. That's going to look something, well, maybe like this. So what's going to happen is we're going to have, the diffraction effect is still there. But the diffraction effect now is not a pure diffraction, it's a diffraction envelope. And within the diffraction envelope, so we'll say the diffraction now, the effect of that is to have these slits, these peaks on these slits for multiple slit. They're not all going to be the same intensity because these different multiple slit effect peaks are going to end up at different locations in terms of the diffraction peaks. So 2 different sorts of effects. There's multiple slit interference effects going on, diffraction interference effects going on, and the way the intensity, the overall intensity effect will show up is we'll have some number of multiple slit interference, but that's going to be modulated by this diffraction envelope. So again, it's stuff, we've seen this in lecture, we've seen this in the text, we've seen it in homework. Should be, should be getting more and more familiar as we move along. Now, a couple of other items I want to point to here. This is our setup for all of this interference effect. In all the homework problems, all the examples from lecture, we start out with the slit pattern, the barrier with the slits, with light incident. And then what we're going to have is light ends up heading out of these different directions. We have a length or a distance between the slit pattern and where the screen is located. And then we have a perpendicular distance along the screen. Now, another item that I'm assuming here is that all of these slits from the multiple slit are the same intensity. There's 2 possible reasons for that. One of the possibilities is that the entire pattern is all contained within a really small angle. so that these different peaks that show up along the screen. So there's going to be different M values. These are so similar, the distance, that we don't really have an intensity drop-off. Otherwise, if we had a flat screen and we kept going to larger and larger angle, the intensity would drop off among the peaks, not just because of diffraction, but also because it's getting longer and longer and the light gets a little more spread out. Now, a way we could get around that, one that we talked about in lecture, is instead of having a flat screen, we can have a circular screen. But today in lab, we have a flat screen. So we're going to be working with a flat screen, and we're going to be doing measurements of X, and we're going to have data tables that look like this. So here's an example of what our data tables are going to look like. This is going to be our direct measurement. We are directly going to measure X. Now I left something out. Oh, I wish I would have done. Let me change this real fast. Let me put theta is fine. Theta is fine. But then I got to get an M or an N value in there. So I'm going to need, like on this example right here. Let's say that this is an example. I'm looking at the multiple slit effect, and this is M is equal to 0. M is equal to 1, M is equal to 2, M is equal to 3. We want to try different M values. So, actually this works fine. This works fine adding the M here. I want to put the M at the front. So I think that's going to be fine. So I'm going to say there is M and X are the direct measurements. So I have to be able to look at an interference. Let's say I'm looking at this interference pattern, and I measure the distance from the center of the 0 out to the center of peak number 3. Well, in that case, M is equal to 3. So I'm going to say M is equal to 3. Now I can get my ruler out. I'm going to get out a ruler and measure. Let's see, where did my ruler go? I think it was right here. I'm going to find my ruler, and we actually have some other rulers here. Okay. I found one. So here's a ruler right here, and I'm going to get my ruler out, measure that distance, and that is going to go into my X measurement. So, I could measure M is equal to 1, M is equal to 2, M is equal to 3. I could get some X values for those, knowing that L is equal to 3 meters. Well, I can say that the tangent of theta is X over L, for example. I can use a little trigonometry, and that's going to allow me to figure out the angle, and I don't need this other M value anymore. Oh, let's see, what else did we have there? Theta, and I can put the wavelength in. I guess we really can just do, I'll just say that we're measuring D. Okay, I'll erase this one. I think, I hope that made sense. And so I'm going to pick an M value, measure the X, determine what the angle is, and then the wavelength. Oh, we're going to need a wavelength. What are we going to use for the wavelength? Well, it turns out that the lasers we're going to be using a helium neon laser. Helium neon lasers we put a mixture of helium and neon into these lasers, and there's a series of quantum states. And in any case, we end up generating a laser effect, and the wavelength for that is 632.8 nanometers. So there you go, 4 significant figures. So that's going to be the wavelength throughout for all the measurements. We'll take a look at the laser here in just a minute. So we got a laser that's coming up. We know what the wavelength is. Let's look at our formulas here. Now for diffraction, something to keep track of here is for diffraction, the integer values of n are zeros, right? So if I'm doing a measurement with diffraction, maybe I'm measuring from here to here. You know, n is equal to 2, and x is that distance. When I'm looking at the screen, I'm measuring from the center of the central peak out to where there's a minimum. All right. So you guys can pick, I mean, which values of n and which values of m you want to work from based on what the interference patterns look like. So pick the interference patterns that seem like they're the easiest to work with, or if you want to challenge yourself, pick some more challenging ones and see what that works out to be. But now that we've got the wavelength written down, and we've determined the angle, and we know the n and m values, we can solve for A, we can solve for D. Now, what this chart is telling me is, when I'm solving for A, I'll just come over to these purely diffraction examples and get some A measurements there. Coming down the center here, I'm going to measure D on all of those. Now, we could go in and try and measure A, but I'm going to say we're not going to worry about it. Okay, so if we get the D measurements, that's good enough. We could go after the slit widths by looking at the diffraction envelope, but I don't know, we'll save that for the midterm or something like that. So let's see. When we get to this last column, column E, oh, we never did column D, did we? We got to go back and talk about that. Column E, we've got two slits here, and so for that we're going to go for the distance D, and then finally for column D, what we want to do is we want to get photos taken of a really nice looking 2-slit, 3-slit, and 4-slit example. So these are just photos that need to get taken. I guess that means I have to take the photos because I'm the lab partner for everybody. I'll take the photos for those and make those available, see what those photos look like. I think that's everything. Let me mention this too. What I'm also going to put in the notes that you'll find on campus. Everything's on campus, right? So you're watching this on campus, and everything else should be on Canvas right along with that same module. What I've got is, I don't know if you can see this, but this is the instructions manual for how these slit devices were manufactured. So I'm going to send you all the information on this, and I'm going to let you guys do some of the calculations. What you can do is you can start from the manual. The manual doesn't give you accepted values quite as simply as you might expect. It would be nice just to have the accepted values given, but it turns out they make you go through some calculations on here. Anyway, it's good exercise to go through. So I will include that information along with the notes for the lab. Let's see, what else do we need to do here? I think we're good. So I'm going to turn the lights off. We can come back to this if we want. I'm going to turn the lights off, and what I'm going to do is redirect you guys over here. So what I've got, I guess I shouldn't have turned the lights off. Well, you guys can see it. What I've got now is I've got a laser set up on a table with a stand. I'm going to turn the lights back on. So here I've got my helium neon laser. It's turned on. You can kind of see what it looks like here. And then what I have in front of it, what I've placed in the path of the light, is one of these little slit devices. So that's got all those different patterns. Right now I've got it going through C1. It's the column in the middle, and it's the one at the top. So that's an example of C1, and you can kind of see, don't look into the laser, and you can see that. Now what's on the other, oh look, it's the lab room. What you can see on the other side over here, oh look, it's more of the lab room, is I made a screen on the wall, and now I am going to turn the lights off. So here go the lights, and
Ooh, there's an interference pattern, right? So you can see that I'm counting 1, 2, 3, 4, 5, sort of bright stuff in the middle. And they're sort of evenly spaced, and then they get dimmer. Now, what this is showing us is that we have, the ones in the middle are part of the, actually, if I stand back here, I mean, I can kind of see this in the viewfinder. I don't know if you guys can see this. But if you stand back, you can kind of see the diffraction envelope. See how there's a whole series of spots, and then those central 5 are within maybe the central maximum. And then it gets dimmer. There are places where things kind of dim out, and then they come back a bit. So you can kind of see that diffraction effect. And then you can see the multiple slit effect. So on this, what we're going to do is we are going to make measurements. We're going to identify, that central one is m equals 0. So that's m equals 0, m equals 1, m equals 2, m equals 3, 4, 5. We got a whole series of different m values that we have right there. Let me place this camera here and see if I can keep it going with that interference. Yeah, kind of. I guess we need to make this a little higher. Okay, so that's what the interference pattern is looking like. Now, from that, I will be right with you. I just have to find it. There it is. I knew it was here somewhere. Remember, I'm a good lab partner. All right, so what we've got here is I got my ruler out, and I'm going to get somebody to turn on their flashlight so I can read it. But then what I've got here is I've got an m equals 0 in the center, m1, m2, m3. Now, if I measure from m equals 0 out to, say, 2, 3, 4, 5, if I use a larger m value, I might get more precision. Right, so I probably should get here and write some of these down. So, and that's my intention. What I'm going to do is I'm going to go in and let me see if I do have a light. This seemed easier before. So I'm going to shine a light on that. It looks like from the 0, oh, I actually can see it. From the 0 out to n equals 1, I'm going to call that 1.2 centimeters. Okay, and then out to n equals 2 is going to be like 2.3, 2.4. So this is doable, so I can do this. Okay, now these I said were the easy ones, right? So let's see what some of the harder ones might look like. I'm going to move this over to some of the pure diffraction. So I am over here shifting this around. Let me see what a pure diffraction interference pattern looks like. And there it is. Okay, and that one actually, that's kind of hard to see. This is, I tried to pick out the ones that were the most dramatic. I think this is A4 that we're looking at right here. So, oh, this one's beautiful, right? So here's A4, and you can clearly see where that central maximum is. That just cuts off really nicely. So I can see the integer values. There's an n equals 1, 2, 3, 4, 5. And this is just pure diffraction. There's only one slit. And so it's just that diffraction effect. Okay, so I'm just going to sit here and marvel at this a little bit. Now, when I do the measurements, identifying where the center of the central peak is can be hard. So rather than go from 0 to 2, what I could do is I could go from, let's say, n equals 2 on this side to n equals 2 on the other side. Now that would give me, that would double the value, that would be 2x instead of just x. That would be 2x, but that would probably be a more accurate way to do that. I think that's what I'm going to do. So I'm going to suggest to the group
that we go from, say, m equals 1 to n equals 1, and then I guess I'm calling these n2 to n2, n3 to n3, do a series of measurements on those, see what we end up with. Okay. All right, that's the plan. So that's what the single slits look like. Now, I'm going to come over here, and I am going to take a look at some of these double slits. Now, I want to see some of the ones that were assigned, so I'm going to drop this down so I can see which ones were assigned. I guess this one was assigned. This is E2. This is what E2 looks like. And so I think I've got that lined up pretty well. This is a little tricky. I mean, what I've got is there's a diffraction envelope right here, it looks like, on these first three. So that's like n equals 0, n equals 1. Now, if I want to use the zeros here, I should use the half integers, but that's not a bad idea. I'm thinking that the zeros may be easier to measure than the peaks. Again, when I've got a peak, it's harder to see. Okay, so that's an example of two slits. I'm going to look at one more two slit because I'm just curious what this next one's going to look like. I should stop being curious and just get the lab done, but instead I'm being curious. Here is one also with two slits. Yeah, that is interesting. So these are a little trickier. There's a whole series of peaks in there. I don't know if you can see all the detail in those. I'm hoping you can. Okay, so I'm going to move on because what I want to do is I want to get my pictures taken. Remember in column D, the plan was to take a picture of two slits. So what they've done in column D is they're all the same width, and then they maintain the same distances, but they keep adding more slits. Why am I saying nothing? Okay, there it is. Okay, I'm looking at that picture. Do you think that's going to get me full credit? Yeah, I think it's a good picture. I think that is going to give me full credit. So I think what I'm going to do... Now remember, when we have just two slits, let me get my phone set up here. What we are guessing that we have, here we go. Oh, that's got some real problems, huh? It is creating, it should be something, you know, it's supposed to look like a cosine squared function. Anyway, I think that's still going to give me full credit, although I'm beginning to worry about the camera on my phone. So this is my photo for two slits. I may have taken a couple photos. And let me go for three slits. Okay, so this should be three slits. What we're trying to see with these, in particular, what we're trying to see is the intermediate peaks. That's the idea here. 2, 3, oh, and this is, I don't know if my camera's going to get this, but this looks perfect. Okay, so what I've got, I'm hoping this camera's got it. If you can take a close look at this, there is a large peak, and then an intermediate, and then a dramatic peak, intermediate, dramatic peak, intermediate. I'm going to zoom in on that just a bit, hoping that you guys might be able to see that from the video itself. I'm losing focus on it. Oh, that's too bad. All my cameras have a difficult time showing this. It looks perfect just visually. I'm going to try one more time. Can you guys see those intermediate peaks? Right there it looks good on my viewfinder. And right there it looks good on my viewfinder. And I know I'm supposed to be able to... is the autofocus that is
failing here? Maybe that's it. I don't know how the focusing is done on these cameras, but okay, I am going to say that's a nice view for 3 slits. Let's go for 4. Now, if we have 4 slits, how many intermediate peaks should there be? And there should be 2 in between. Midterm's coming up. You guys are supposed to know this by now, right? So if there's n slits, there will be n minus 1. Is that right? Intermediate. Oh no, it's going to be zeros. N minus 1 zeros in between. And n minus 2, I guess I have to get ready for the midterm too. Okay. I think it looks good from here. Let me look closer. And yeah, it really looks good. So I'm hoping the videos are going to pick this up. Let me see if I can come in and get this. I was having better luck before. I'm going to come in and see. Oh, that's not bad. So I don't know if you guys can see this, but there were, now it's just going blurry. But there were those 2 intermediate peaks. I've got to get better at controlling the... I'm going to get a picture of that. I don't think I got a picture of the last one, right? So I got to go back and get another picture of that. I will do that. At my own convenience, I guess. Yeah. So, well, now I realize how difficult this really is to get a good photo of this. I'm going to try getting a real close-up and see if it works. Okay. Anyway, that's it. That's kind of the measurement. So we've looked at examples of all the measurements that we're going to do on this, and okay, I'm going to try and get, oh, maybe I had a picture of this. I don't remember. I'll go ahead and take one more. Okay, so I've got pictures of all of them. Not as good as they should be. If you guys were here taking pictures, I'm sure that some of you would know how to get a higher quality video photo of this. Anyway, this is the idea. Now we've got enough information. We can go back and get all the A values. We can get all the D values, and then what we want to do is do explanations. So I want to see some phase diagram explanations as to why the pattern looks like this. So I will, in the notes, in the slides for the lab, there'll be a series of items that you want to make sure you include, and one of those things that you've got to include is, hey, why does it look like this? Why do we have these intermediate peaks? And the explanation is in terms of phasor diagrams. All right? So that's the video part of today's lab. So get to work and get through all the tables and get everything written up. If questions come up, stop by and ask me. And we'll take it from there. Okay, I've got a lot of office hours, so do not hesitate to stop by. I'm just, just stop by office hours. If you guys have questions, stop by. All right, have a good day. Bye.